Hi class. Alright, this is the beginning of class 5. I forgot to start the tape, so I guess my punishment is I'm going to do a quick intro for class 5. I did notes for this class, actually slides. You can look at them on the Blackboard website under course materials, class slides, class 5 slides. So, in class 5 we talk about regression. I'm going to direct your attention to the bottom of page 1. You can see that I've got a scatter diagram. On the x-axis is time spent online. On the y-axis is money spent online. With regression, we try to establish a relationship between two things. We'll call the x variable, time spent online, the independent variable. So people spend a certain amount of money on, a certain amount of time online, and we are attempting to predict how much money they will spend online as a result of that. So in this example, we've collected 6 pieces of data, and you can look at the dots. You can see, there's each of those represent a person, how much time they spend online versus how much money they spend online. And you can imagine that we draw a line through that data that seems to fit the data. It's not going to be a line that will fit perfectly, but it's a line that will be our best estimate at what that relationship is. Now, what I did in class and what I'm going to do again is I'm just going to preview the key concepts that we will go over in class so you can think about intuitively how that material, just intuitively, the material intuitively, and then what will follow will be filling that in with the numbers and the equations and such. So we're thinking about how we might fit a line in that data. It's not going to fit perfectly, and that's the first key point, is there's going to be some error. So if we were to draw a line through that data at the bottom of slide 1, there would be some points would be a little above the data, some points would be a little below the data. The line of best fit is going to reduce those errors as much as possible, but there's still going to be some error, and we'll call that unexplained variation. It's not explained by the regression line, it's explained by other factors. We don't know what they are. All we know is that time spent online does not perfectly explain how much money is spent online. So that's an error. We don't want to look at just the negative side. We want to look at the positive side too, which is that this regression line that we just drew, that I just drew, all right, I'm going to draw it. And you can print out the slides, you can draw your own. We will look at how much variation there is total, right? Before we even draw our regression line. You can turn to the next page. Actually, yeah, on the next page, top of page 2, there's that regression line that I drew. You can draw too. Bottom of page 2, there's a straight line across, average money spent online. So that's taking the average amount of money that everyone spends of those 6 people. So that's just straight average. And you can see we have deviations from the average. The first dot, as you look on the left side, is fairly close to that average. And if you look over on the right side, you see one that's really high. Right? You're like, wow, why is that so different from the average? Well, what the regression line shows us is it explains some of that difference. So if we were to, without the regression line, just say how much difference each of these points are from that average money spent online, that would be the total variation. So the bottom of page 2 is giving us an example of total variation. And then we look at the top of page 2, we draw our regression line, and we explain some of it. So some of that variation is explained. Like the reason why that dot that is to the far right-hand side is higher than the average is partially explained by the regression equation. So bottom of page 2 gives us a sense of total variation. Top of page 2 gives us the explained variation. But there's still some error. I mentioned earlier, as we find that line of best fit, it's not going to fit the line perfectly. So there's three things. Total variation, get a sense of that at bottom of page 2. The amount of explained variation, top of page 2. And then the fact that that line doesn't quite fit perfectly, unexplained variation. So what we can do later on in the class is we can say the amount of unexplained variation divided by the total variation, that tells us is, say, 10%. So 10% of the data is not explained. 10% of the reason or factors that go into money spent online is not explained by time spent online. Conversely, we can look at how much is explained. And we might have a pretty good regression equation which would explain 95% of the variation. So how much money someone spends online can be explained 95% by how much time they spend online. Okay, so that's step 1. We'll call that performance measures. Step 2, or the second thing we'll do in class, is we'll think about the fact that this is just a sample. These are 6 points of sample data out of a population of, how many online users do we have? 4 billion. So we need to understand that we can't say this is a conclusive, that is the regression line for the whole population. There could be variances. We could have gotten the y-intercept a little bit wrong. We could have gotten misleading data for the slope. So those are the two things. You can see that regression line. 1, where does it cross the y-axis? As we look at the whole population, there could be a problem with the sample data we've collected, so we may need a confidence interval to explain that. Step 2, or the other thing, is the slope of that regression line. That's based on a sample of 6. The whole population, we can't conclusively say that that's what it is for the whole population. We need a confidence interval to account for what the slope of the regression equation for the whole population would be. With that, we will do a hypothesis test to test whether or not the slope is significant, whether or not it tells us something significant. Now in this example, we're saying that the time spent online has a positive relationship to the money spent online, meaning the more and more time a person spends online, the more money they might spend online. So that just means that the line, the regression line, top of page 2, is sloping up as we move to the right. So we think there's a positive relationship. But when we infer that sample data on the whole population, we can do a hypothesis test where we'll assume there's no relationship. It's just a straight line. That will be our null hypothesis. No relationship between time spent online and money spent online. And if you remember from class 4, the alternative hypothesis will be something that we will need overwhelming evidence to prove. So null hypothesis, no relationship. If we find overwhelming evidence that there is a positive relationship or a negative relationship, then we will reject the null and say, oh yeah, there's a significant relationship. Okay, so that's the second section of material we'll cover. The first was performance measure, variation explained. The second was what we infer from the sample data on the whole population. Third was the expected values for y in the whole population. So, in addition to the fact that we've just taken a small sample and we need a confidence interval for the whole population, there's also something else. The population of internet users has variation within itself. So, of all the people who spend, say, 15 hours a week online, they don't all spend the exact same amount of money online. In fact, I'll just skip ahead because it's easier to do when I'm not doing the PowerPoints. I'll just skip ahead here to the bottom of page 12. This is when we get to the inferential side of regression, what we infer about the whole population. You can see that we've got x on the horizontal axis, y on the vertical axis, and we've got data. Let's just assume it's time spent online on the x-axis, money spent online on the y-axis, and you can see it's moving up as we move to the right. Now that line, the actual line in between all those dots, that is the exact specific regression equation for the whole population. But those dots, those are the whole population. The dots don't conform exactly to what we would expect, or what we would predict as the expected value for the regression equation. And that's the way it is. Two people who spend the exact same amount of time online, they do not spend the same amount of money online. And the issue there is there's just other factors affecting it. It may be income, it may be how impulsive the person is. So if we're going to estimate how much time does Carlos spend, or excuse me, if we're going to estimate how much money does Carlos spend online, if he tells us how much time we spend online, then we can tell, we can determine some part of the answer to that question, but he could be any of those dots. Okay, so that was the third part. First part was performance measures. Second part was what we infer on the whole population once we take a look at the sample data. And the third part was related to that inference, but it was just to remind you, make you aware that there is no exact y value that will be outputted if we input an x value, because different people spend different amounts of money, even if they spend online, even if they spend the exact same amount of time online. Okay, I feel like that took a lot longer than the introduction in class. Hopefully it was useful and not confusing. So let's direct our attention then to the bottom of page 3. Simple linear regression means one independent variable, one dependent variable. Linear means there's a straight line relationship. There are other types of relationships, but we'll just look at a straight line relationship. And today we'll look at one independent variable, one dependent variable. Next week, we will look at multiple independent variables. So there could be several things determining how much money you spend online. It could be how much time you spend online. I think I just said this like 2 minutes ago, but how impulsive you are, how much money you make, how embarrassed you are when you have out-of-style shoes, all those different independent variables which will spit out money spent online. That's multiple regression next week. Performance measures, that's the explained variation, unexplained variation. Inference, which is what we infer in the population. Estimating the intercept and the slope, that's again inference. So if we have a sample, we may have gotten the slope or the intercept wrong, and so we need a confidence interval for that. Furthermore, we can do a hypothesis test to see how confident we are that there is a meaningful slope, that there's a slope that can be represented statistically. And then estimating values of y. That's that thing I mentioned with the estatements and how people are different. And then the last thing, complete printout for simple linear regression. Actually, I forgot to do this in class. But I will tell you the page number. All right, the printout is on page 425. So you can look at page 425 and you can see how the printout works for everything that I talk about in this section of the video and the class section video. Essentially, you don't have to come to class, you just need to look at that printout. That is an exaggeration. You need to come to class so you can understand what that printout means. but you won't have to do the calculations because you can look at the Excel printout. Okay, moving on to page 4, regression. That's a definition. Regression analysis attempts to identify a mathematical function that relates two or more variables so that the value of one can be predicted from the value of other. Value of how much time you spend online can be predicted. Value of how much money you spend online can be predicted by how much time you spend online. Simple means one independent, one dependent. I talked about that. Multiple is one independent. Multiple would be two or more independent variables. We'll do that next week. Straight line means linear connection. You got it. Bottom of page 4. Once we take a sample, we will be able to calculate the slope and the y-intercept. And we will be able to calculate an equation. Y equals A, which is the intercept, plus B, which is the slope, times X. So we will input X into that equation, and it will spit out our predicted value for Y. So we will input time spent online, it will spit out money spent online. And take a look at that slope B, recall from algebra. The slope is the change in Y for a 1 unit change in X. So 1 more hour spent online means $3.50 more spent online. So you spend an extra hour online, you spend an extra $3.50 if the slope is 3.5. Okay, let's move on to page 5. Basic simple linear regression. Basic concept. Simple linear regression uses one independent, one dependent, produces a straight line. Indicates to what extent the variables are associated. It does not show cause and effect. This is one thing statisticians get really funny about. We cannot say that the amount of money you spend online is caused by the amount of time you spend online. You can only say that there's a correlation between those two. Or you can say that we can predict money based on time spent online. But we can't say there's a cause. We need to think that through carefully before we even try to make a statement like that. Statisticians don't really get into cause and effects as much. But the data can be very powerful and very useful even without being able to say the cause and effect. Scatter diagram, which is the diagram we used in the previous slides. We'll plot everything, fitting a line to the data. All right, so we talked about this. Generally, the data will not fit the line perfectly, but we'll do the best fit. All right, so bottom of page 5, we are ready to get into the performance metrics. So we've got our same scatter diagram. We're going to find that line that makes the sum of differences from the line 0. So take a look at the first point. As you look to the left, it's a little bit higher than the line. The second one, as you move to the right, it's just a tiny bit lower than the line. So maybe the first one is like +3. Maybe the second one is -1. So now we're at like 2. And then as we keep adding those up, the line of best fit is going to sum to 0. Yes, it is possible that that line, the deviations from the line in the sample data, will sum to 0. What we want to do as statisticians is, instead of having data that sums to 0, is we want data that tells us something more useful. So we are going to square all those variations. So they don't cancel each other out and just equal 0. The squares tell us the magnitude of the variation. For example, we could have data that's really high and it could be canceled out by a data point that's really low, and that would be more variation than 2 data points that are just one above, one below. They both sets of data sum to 0, but if we square the differences, that gives us more meaningful information. And we're going to call that the least squares criteria. We call it later the sum of squares error, SSE. Later on, SSE. For now, we'll just call it the least squares criteria. I'm at the top of page 6. Identifies the best fitting line as the line that minimizes the sum of the squared vertical distances of points from the line. Okay, so we want that as small as possible. what we will later call the sum of squares error. So errors, how much above or below the line they are, squared, add that all together. We want that as little as possible. And if we didn't square them, remember they would all add up to 0. Okay. Now, bottom of page 6, we have equations based on, say, these 6 points of data or 4 points of data. We could calculate the least squares criteria, and we could come up with the slope. And those would be the equations at the bottom of page 6. So it's the slope b equals n, number of samples, times the sum of x times y. So every x times every y, sum it all together, minus the sum of all the x's. So add up all the x's, sum of all the y's. I do all this towards the end of class, so you can just look at it there, but it's just put the numbers in Excel, add them together, or multiply when you need to. I recommend that you do this once or twice with Excel just to get a feel for where these numbers are coming from. And then after that, you'll just read the printout and we'll never calculate it again. So we have equations where we can calculate the slope and equations where we can calculate the intercept. All right. Once we do that, and we're at the top of page 7, we have an estimated regression equation. So y, that little hat, little thing above y hat, we call that y hat. That's the predicted value for y given some value of x. So you tell me how much time Joey spends online, I will tell you the predicted amount of money Joey spends online. And that's y hat equals a, which is the intercept, plus b, which is the slope, times x. So you enter x, I multiply that by the slope, add a to it, boom. Okay. So I guess we're still warming up here, intro to simple regression. Now we're getting into the specific performance measures. And remember I said that was explained, unexplained, that type of thing. So bottom of page 7, we went over, I guess we didn't go over unexplained. I guess we did, we went over like some of the data is explained by the regression equation, some of it is not. So unexplained variation, 2 down we have explained variation, 3 down we have total variation. And it turns, and so when we calculate the ratio of explained to total, we get the coefficient of determination. So if the explained data, sum of squares is like 490, and the total variation of sum of squares variation is 500, so 490 over 500, that's like 97, 98%. You would say the regression equation explains 97%. Another, and we'll talk about that more. Another important metric is the correlation coefficient, which is the square root of the coefficient of determination. And with square root, it can be positive or negative. So we'll say that there's a positive relationship or a negative relationship once we look at the correlation coefficient. And with the example we used earlier, we were thinking that there was a positive relationship. So more time spent online equals more money spent online. It could be negative. More time spent online could mean less money spent online. Like people who spend their whole lives online never buy anything. They just stay at home and surf the internet. Or maybe there are people who know how to find deals because they spend so much time online, so they spend less money online. So that would be a negative relationship. All right, and the only other thing I didn't mention at the bottom of page 7 is going to be the standard error of the estimate. This is going to be our basic standard deviation term for the line of best fit that we calculate based on the sample data. So we'll have our sample data, we'll calculate that line, and we know that it's not going to fit the data perfectly. There are some variations. So we're going to use that sum of squares error, and we're going to divide by some number and take the square root of that, which is going to give us our basic standard deviation based on this sample deviation. Standard error of the estimate. I think we explained that. I explained that more carefully. All right, so here we are. I'm 24 minutes in I'm at the top of page 8. Take a look. I want to do this. So we're top or bottom of page 8. I haven't decided yet. So, okay. Yeah, let's look at the top of page 8. Okay, so we have 6 points of data. There's something represented on the x-axis, something represented on the y-axis. Now that straight line that has y with a bar over it, that's the average y value. So if you can say, look at that first point, it looks like it's about 1, 2, 3, 4, 5 notches up, and that's the average. The second point is 2 up. The third point is 5, 6, 7. The fourth is like 3 up. So we just add those all together and we average them, and that's going to give us that straight line, y bar, y with a bar on top of it. That's the average. The line that is sloping up to the right, it has a y with a little hat on top of it. That's y hat. That is the regression equation that we're going to calculate based on previous formulas. So let's look at that point of data at the highest one. It's the almost as you moved from left to right. It's almost to the far right, but it's not quite. It's the highest point of data. So the difference between that and the line labeled y bar, that is the total variation. Now, if you were just taking a straight average of, say, money spent online, that could be the y bar. And you'd look at that really high point of data and say, gosh, why does that person spend so much money on why is that person so high above the average? Well, we can explain part of it with the regression line, y hat. You can see that the regression line is closer to that point of data than y bar. So the part between the y hat line and the y bar line, that is explained. Explained. The part above the y hat line and all the way up to that point of data, that is unexplained. Unexplained. That is summarized on the slide below. The long line is total variation. The one between y bar and y hat, which is y hat minus y bar, that's explained. That's what we predict from the regression equation. Above that is unexplained. All right, that's variation over and above what we would expect based on our calculations of the regression equation. Okay, let's take a look. Top of page 9. Here we have the sum of squared error. Now I mentioned that we call this sum of squared errors, sum of squares error, earlier when we're using the least squares criteria to calculate, when we're using the least squares criteria to calculate the line of best fit. So that is unexplained. Okay, so that's unexplained. Let me backtrack a minute. I remember I did something in class before I confused you online. So, okay, let's just go back to the top of page 9. So we've at the bottom of page 9. So we've got the total variation. Is that, you know, yi, which is an individual value for y, minus y bar. And then we've got explained variation, which is y hat minus y bar. And above that, we've got unexplained variation, yi minus y hat. Okay, so a very important metric is how much of the difference, how much of the variation can be explained with the regression equation. We will find that by taking the explained variation divided by the total variation. Okay, you with me? Explained variation divided by total variation. Let's skip ahead to the top of page 11, and that's going to give us our coefficient of determination. also known as r squared. So explained variation divided by total variation. Okay? I just want to jump ahead and make sure you're clear on that before we move on. Explained over total is the coefficient of variation. Again, I think I used an example. If our sum of squares for the explained variation is 490 and our sum of squares in the total variation is 500, 490 divided by 500 gives us like 97, 98%. This regression explains 98%. Okay. So we are back to the top of page 9. And then, I'm not sure how much I stressed this in the video so far, but so the sum of squares error, I think I remember talking about it in the video. So that's the error. The line doesn't fit perfectly, so there's a little bit of a difference between the data points and the actual line. We square that, we sum it all together. And then let's skip the bottom of page 9 for a minute. And then let's look at top of page 10, sum of squares regression, which is how much of the data is explained by the regression. We add that all together. It's just the y hat minus y bar. And you can look back, y hat minus y bar, it's that explained. We square that for every data point, add it all together, gives us how much data is explained by the regression. And then the same thing, bottom of page 10, sum of squares total, which tells us, from the actual y to the average y. So find that difference, add it all up, square it for everything, and that's going to give us total variation. So we've got total variation, we've got explained variation, we've got unexplained variation, and then I think it picks up the video you're about to watch. Picks up with standard error of the estimate, which is our basic standard deviation term for the regression line. So have fun watching that, and I will see you in class.